right. I think we've got quite a few attendees coming in here. People can join later on, so we'll go ahead and get started. Introduce myself, and then I'll hand it over to you. My name's David Kermgard. I'm a principal sales engineer slash developer advocate slash jack of all trades at String Native. We're the company behind Apache Pulsar and a cloud-based streaming solution. And joining me today is Daniel Davis, and I'll let him introduce himself.
Thanks, David, for the introduction. I'm Daniel Davis. I'm the co-founder of TrustGraph. TrustGraph is an open source agentic platform, which, that's what does that mean anymore these days? We really focus on being everything between your data and the application layer, which a lot of the genesis of TrustGraph came about from our expertise in knowledge graphs and using knowledge graphs as a way to structure unstructured data and then being able to retrieve that for improving the accuracy and responses of AI models. As the platform has evolved, it's become a lot about how do we deploy the platform, where do we deploy the platform, containerizing it for cloud, for local on-prem, even looking at maybe edge applications, which is something we're going to talk about today. And of course, it's built on top of Apache Pulsar, has been from day one, and that's one of the key enabling features of TrustGraph. A little bit about myself quickly. I've had a pretty diverse background, which you're probably going to figure out in a couple of minutes. Spent a long time in US DoD aerospace, working with large fleets of very complex aircraft. Spent some time in the autonomous vehicle industry, kind of because of my aerospace experience. Been doing stuff, with cybersecurity, a lot of stuff with risk, and also safety engineering. So I've always worked in domains where there was lots and lots of text and lots of documents and lots of information that has to be cross-referenced and understood from very many different perspectives to be able to accomplish a task. And that's kind of led me to everything where we are today. Should I begin?
Please, we're excited to get started. What are we going to be talking about today, Daniel?
Well, the story in three parts. I'm going to talk about my experience dealing with siloed data and the immense pain that caused, and a clash of different perspectives. Why the old way and the new way don't really work well together, and the reasons why and why we need to solve that problem. And then I want to talk about why in these applications there's a lot of challenges on actually leveraging AI, even more so than some of the other applications where people are building AI solutions today. So my past pain, working with the C-130J with the United States Air Force, a particular aircraft that I was responsible for had an engine generator problem. So we had this system on the C-130J that would basically give you a readout of error codes. And once you looked at that error code, you then went to a manual that says, this is the process you do to resolve this. And some of these processes could be quite lengthy. And then you become, what happens when you go through this process and it doesn't solve your problem? Well, that becomes an issue. And that's exactly what happened with this aircraft. Is they went through the processes in the manuals and it never solved the problem. Sometimes the problem would manifest itself in a different way. And it got to the point that this aircraft was sitting in a hangar for close to a year. I remember 6 months at least. I think it was longer than that because of one error code. And what this really is because of is you had data everywhere. So we had this data from the actual aircraft system, which in this case, wasn't even OTA. This actually had to be physically taken from the aircraft and loaded into a system. And somebody actually had to download the files and then review them. And then you had to actually translate those error codes to what they meant, which was another set of documents. Then you had the maintenance manuals, what you're supposed to do when you get an error code. And you have many, many processes scattered across. You could fill quite a large room with all of these manuals that are hundreds of pages of each. And then you start getting into the really important issues, the history. We had 10-page documents written by all the different maintainers who had been dealing with the issue for the past few months. And you have to read about what their experience was, what they did, what they saw, what happened after they followed this process, what did they try, why didn't that work? And most importantly of all, there was a huge amount of tribal knowledge. And some of this was in emails where somebody didn't write it in a report because there was no even central repository for, hey, I wrote a maintenance report. It goes in this system so everybody can see it. So you had emails, internally, even at Lockheed, between, some support engineer in this market had seen this issue and, communicated it to another one of his colleagues. But all of this information was needed to solve a very, 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 very simple problem. And that essentially a connector in the wing brake where the wing joins the fuselage had pins that were too short, and occasionally they wouldn't make a good connection, which essentially it needed to be like reseated in the actual where the connector actually sits in the actual metal of the aircraft. That's it. That's it. That was the entire problem. But it took close to a year for people to really comprehensively figure this out because all this data was scattered. What did we do? Well, I read a lot of reports because what else could I do? And my Lockheed team, who actually, I don't know if Harold is on this. I invited him in. Hopefully, this is not bringing back too painful memories, Harold. Shout out to Lockheed. I did check with them to make sure it was okay to talk about this today. Um, we sat around reading reports and emails. It was an entire team of us. And then we actually flew out to Texas where the aircraft was to, stare at it and then explain to people and point at reports. So it was all reading and then communicating. And if all this were connected in a system that allowed to be able to read for us and understand and be able to pull all this data in a connected way, we could have prevented an aircraft from sitting in a hangar for the better part of a year. And that brings us on to part two, a clash of networks. The old way of designing, whether it's an aircraft, a car, even industrial automation, anything where you have technology, software running on hardware in a deployed environment. Initially, it was all point to point, physical wires. We physically wired these things together. Then we began maybe, more of a motherboard type philosophy where it's all integrated on a single platform that's connected by different kinds of bus architectures potentially, which kind of brings us to where the next iteration of these kind of networks and that's in bus networks, because point-to-point networks don't really scale, do they? Because every time you want to add a new system, you have to run new physical wires. And then depending on how that new system interacts with other systems, you may have to change the wiring to old systems. That could be extremely painful. So we developed bus architectures where you have a single data rail layer that you could just plug into. And for all of those out here, all of our Pulsar fans, you're probably thinking, well, that's okay. I get where you're going now. Well, this is the old way of doing things. Well, it's not so old. It's still done that way. If you look at, vehicles, CAN network, the CAN bus is very similar to this. Matter of fact, CAN is very similar to, MIL standard 1553, which again, I was working with an aircraft like the C-130J, and so many aircraft and so many applications still use that bus network today. So this is kind of a physical way of doing pub sub in a way, because you have a central data layer that you can then just plug network participants into. In this case, it's just at a physical layer, not a logical layer. And these, and this is going to become a term that I'm going to talk about quite a bit. And there may actually be some questions about this because this may be a term a lot of people are familiar with, and it's quality of service. When you talk about vehicles, especially today, especially modern ones, um, quality of service is really important because you have many different networks on the same vehicle. And sometimes they're actually sharing the same data networking infrastructure, sometimes they're not. One way to think about this is a commercial aircraft. You're probably thinking, um, how, because these things, most of them are fly by wire now. You don't have physical linkages for the controls on the flight deck. That is, a flight controls network. And then you have an infotainment network where you're watching movies and you're probably thinking, well, gee, I hope these two aren't connected. And they're not. Asterisk. We could talk about that in a different conversation. And that's what's called federation of networks, where you have different networks that serve different use cases and different functions. So you have those quality of service levels where I absolutely have to have this data delivered to me. I can't risk losing it. It has to be delivered in X number of microseconds versus, well, this is infotainment. If there's a drop frame in somebody's movie, well, they can buffer it. It's not necessarily a big issue. So that's really important on vehicles. Now, in the cloud world, we haven't necessarily thought that way yet. And I find this really interesting. I was actually shocked. I found a graphic that actually had the OSI model next to the TCP/IP model. Now, the only interesting thing is I typically have always saw the numbers go the opposite way, but I thought it was pretty good. The OSI model is actually how vehicle engineers tend to think about these networks because you control all of this. You control the physical hardware layer, the data links, the actual network, and then how are you actually transporting that data? Um, and if you're using federated networks, you have a lot of networks going on, and that's kind of where things like that we're going to talk about, DDS pub sub comes in. Now, the TCP/IP model, this is kind of more how we think about modern infrastructure, where we're using public networks to connect to API services and cloud. And why is the thinking so different? It's because we don't control the hardware, we don't control the network interface, we definitely don't control the internet, and we don't really even control that transport layer so much. We're kind of specifying what type of transport we want to use, and everything then becomes about the application. It's a very, very different way of thinking when you control the entire stack from hardware to the application versus we're using infrastructure all the way up to the application layer that we don't really have full control over. We can specify how we want to use it and particularly do some configuration, but we don't have control over it. And this is just an example from the FACE standard. This was a consortium I used to be a member of that was trying to standardize all of this for vehicle applications for military aerospace. They saw a big problem in that how we're designing modern software diverges greatly from how we designed software in the past. And as you can see, everything that you're seeing here in this box was up here. Yeah.
Mm-hmm.
There we go. I still haven't got that backwards thing right. Everything in that box, that's on a device, all of those systems. Whereas in a modern architecture and how most people probably have Pulsar deployed, so many of these things live somewhere else. A lot of these lines would be an API to a service hosted somewhere else that's running in somebody else's cloud instance. So logically, very, very similar. But in practice, huge difference in that, this is a physical device where the designers have total control over really everything inside that box. Whereas the way we're designing, I guess I would say modern software, cloud-based software, which I guess, let's be honest, pretty much it is everything these days, aside from embedded. You have very little control over this, except what's inside your sub box. And again, that's really the point I want to make here is that when you talk about um, these old, well, they are old. Let's be honest, they are old. I mentioned CAN earlier. CAN dates all the way back to the 80s, still used on a lot of cars today for mostly the vehicle control. You have a lot of technologies on aircraft. There's commercial aircraft that are still using, oh boy, ARINC 429. Somebody in the chat probably will remember that one. A point-to-point network. There's still aircraft using that in a mix of then trying to put Ethernet on the aircraft as well. So it's just a very different way of thinking that also has to do with, really, really two factors, which this is going to become a recurring theme. The ability to manage the quality of service of the data being exchanged and having full control down to the hardware of the system. And part three, what does this mean if we want to use AI for these types of systems? We already know there's lots of challenges with the AI. The idea that it gets even worse, oh boy. And the first one comes about time scales. If we're thinking about a vehicle and real-time data, we're talking about data that's being updated at the microsecond level. It can actually be much more granular than that. I've seen real-time operating systems where the micro ticks are in nanoseconds, single-digit nanoseconds. If you think, internet time, if you were to ask most modern developers today who develop, cloud-based art, software, real time is not microseconds. No. It's milliseconds.
Milliseconds.
Yeah. We think, oh, that's real time. Two very different ways of thinking. So to people that say real time for an actual vehicle, single digit microseconds, potentially nanoseconds, if we're thinking cloud-based architectures over public networks, we're thinking milliseconds, massive orders of magnitude. And then if we're thinking about AI models, tens of seconds, even the best with the best hardware, even though we kind of get fooled by the streaming responses that make it look like, oh, something's already happening. Well, for it to finish its response, we're still talking probably in tens of seconds, maybe single digits, but still, the biggest models, they can take quite long. And if you give them a lot of context, I've seen Gemini models, the latest and greatest, with a lot of context, still take around 30 seconds to fully respond.
Mm-hmm. Are there other factors when I think about these things besides time, orders of magnitude? I think things like bandwidth, latency, reliability, these things we have to bridge as well. How does that come into these? I'm sure you'll get to it, but doing it on the grid versus off the grid and how you make those decisions, right? How do you span those gaps, right? There's reliability issues with some networks and not others. So hopefully you can talk about that a bit. Yeah.
Sure. Again, I think that comes back to the control issue, is that if
Mm-hmm.
you fully control the data links, you have a much better idea of what the failure rates on these networks are, which is, I know the bit error rate of, mil standard 1553, I think is measured like 10 to the minus 8, I think, because it's a physical rail. When you're talking physical wires and physical connections, the reliability is very, very high. When you start talking about logical connections that are then many, many, many layers removed from the physical connections, which again, we don't have control over the physical connections. Just look at, was it yesterday or the day before, a major Cloudflare outage brought down a big portion of the internet. or AWS US East 1 had an outage. Was it last month or 2 months ago?
Yep.
Major global disruption because you don't have physical control over the data. Now, bandwidth, that's a really interesting one because if you control the full stack, you can think about it in a very different way. You can be much more efficient. So much of the overhead in modern data exchange is because we're having to go through so many layers. There's so much information, metadata or just configuration that has to be exchanged to communicate over public networks. If you're communicating over a network and hardware that you fully control, you can broadcast stuff down it's in hex payloads that are only a few bytes long, and then you just have a lookup table on the other system, like what is this, what is 46AA mean, and you just go to a table and you look it up, and this is all happening in microseconds. You don't have to exchange a lot of information, whereas if you don't have that control and you're trying to create an API service that thousands of people, millions of people can use, and they want to use it in different use cases, you can't be that efficient. So there's a big efficiency gap as well. I mean, that's a very good point, in that designing a vehicle where you have total control, you can tailor everything to just that use case. So you have very, very, very efficient payloads. Whereas when we're broadcasting and using public infrastructure and using APIs for multitudes, unimaginable use cases, we can't enjoy that same level of efficiency. So that's another reason why you can get systems that perform at the nanosecond and microsecond level, because the payloads and the data being exchanged is very, very, very efficient. Which kind of actually gets to what I was. It's almost if you knew what I was about to say, David.
I
It
did.
gets in. I don't know how you did that. I'm scared now. Sampling problem, in that you have real time data, so we know there's a big performance gap in that we have data that's microsecond level versus millisecond and on up. And we have all this dynamic data that's constantly changing. How do we manage that? And I wanted to use a quick example. And I thought, because we're talking about vehicles, I know here in San Francisco, I see autonomous vehicles a lot. Waymo's every day. Zoox has actually just launched their service. I saw them zipping by me just yesterday, and hopefully get a chance to get in one of those pretty soon. I thought, what if you just wanted to use AI to say, be able to connect to one of these autonomous vehicles, and just something as simple as, what direction is the steering wheel turned right now? That seems like a really simple problem.
Mm-hmm.
And as a matter of fact, we even found some MCP servers that will connect to CAN, sort of. It's simulated, but you could actually connect it to CAN. So if you had a vehicle with a CAN bus, you could actually use AI to tell me what's the steering angle. And you would get an answer, and you would think, amazing. There's only one problem. If you look at that actual CAN bus, this is constant. This is just a flood of data being updated every few microseconds. And if you then think about a car, how often are you actually turning the wheel? It's mostly pointed straight most of the time. A turn is only a couple of seconds. So the probability that when you actually ask that question and you go in and you pull that data, because you have to pull a number, give me a value. Respond. If you think the response request way of thinking, I'm asking a question now, give me a response, you're going to get a number, and it's probably going to be 0, because then the LLM has to process this, and we're waiting, say, 10 seconds to get a response. So by the time the LLM gives us a response, is that even accurate anymore? When was it accurate? Because you are just taking a very, very, very small moment in time when most of that data was zero. Because if you look at CAN bus and you look at the data, most of the time it's not very interesting because you're looking at a time scale of microseconds, which also gets to, I always make this analogy of, what does scale mean? And it's when you have a volume and velocity of data. In real time, the volume, yes, no, maybe. The velocity is incredible, absolutely incredible. And so if you have a system that has like a pub sub architecture that's managing all of these federated networks, what better way to start managing that data for our modern infrastructure than getting that in to Pulsar? There are a couple of catches though. In Pulsar, we think about, well, it's not just Pulsar. Let's just be honest. The way we design modern software is typically around request response. That's typically how most APIs work. You're not just sending a command. Whereas vehicle networks, that's the bulk of what's going on the network. It's either just data that's just being consumed, or it's just sending a command that isn't require some sort of exchange. There's no exchange of a conversation like we're having now. Whereas the majority of how we interact with modern cloud-based systems is there's a conversation that's happening, a two-way. I'm asking for something and you're giving me something in return, which is, again, because we're designing systems to be very flexible and serve many, many use cases so that we have to have this exchange. So there's a lot of overhead. So almost all of what's going on in these vehicle networks is almost kind of like what we think of, fire and forget. We just have all this data and we don't want to be able to remember it, except, do we? That's where we get and run into some really, really interesting challenges with we could absolutely map all this stuff. So if we take, DDS pub stuff, and I could go into a little bit about DDS right now. There are differences. It's a publish subscribe system that's going to run on deployed applications like a car. I know a lot of autonomous vehicle manufacturers actually use DDS on vehicle. Very, very common in aircraft, drones, etc., where you have federated networks and you have quality of service requirements. That's kind of the big one, is that's the thing that it does differently than I think modern systems, is that you have this ability to manage. I have data that's absolutely has to be delivered and have to be delivered within X amount of latency, bounding, etc. And then you have data that I care other things about. You have data that maybe I can retry, don't want to retry. And then you have data you go best effort. That's also a term that gets used a lot in this world, is you have stuff that's just best effort. I send it. If it's received, great. If not, we tried. And that's kind of like infotainment on a commercial aircraft. It falls under that bucket. It's best effort. So the tiered quality of service, that's where there's a disconnect. And the other one is, if we go back to the kind of thinking about that OSI model, DDS uses UDP multicast for discovery. And you're probably thinking, what? Again, to us, thinking about developing architectures that are using public infrastructure, that are connecting to APIs we don't own, where there's authentication that has to happen. You're worried about security, encryption, end-to-end encryption, and you're thinking, UDP multicast? Well, again, this is the thinking from, we control the entire system down to the hardware. And these have physical either wires or traces on a PCB where we know where this is getting broadcast. So these systems even exchange state in a very different way. They're doing it on like a microsecond level. I can't remember, was that on this? Yeah, I think it was. instead of storing the system state, like Pulsar does, with Zookeeper and being able to understand who the publishers are, who the subscribers are, what are the topics, and what are the other rules. This is just constantly being updated with DDS through multicast, through just broadcasting, which again, when you have very, very low overhead and you control the entire stack, there aren't really many drawbacks to doing that. So if we want to be able to take data from a vehicle, if we go back to my problem, my initial problem of trying to prevent an aircraft from being sitting in a hangar for the better part of a year and wanting to get data off a vehicle and being able to compare it and understand it in the context of a lot of other data sources, how do we do that? Well, we could say, well, let's redesign the systems on the vehicle for be more modern. We could, and the vehicle people would go, but wait, and they'd have a point because cloud-based architectures and cloud-based systems don't necessarily solve all of their problems. So the solution is let DDS do things it does really well on the vehicle, and then let's bridge it to systems like Pulsar that allow us to now leverage modern infrastructure and the ability to go and find compute where it's available so that we can start crunching all of this data. And in terms of AI, and I don't think this slide is as incendiary as it would have been a few months ago. I think this is, I think people are beginning to get here. I think a lot of people are now visiting this place called reality. LLMs are not these magical things that are going to solve all the world's problems, or at least not anytime soon. Still require a lot of compute. We actually have a full, end-to-end test suite for TrustGraph, and we actually try to find the smallest model that will pass our full end-to-end test suite, and that currently is Gemma 3 27B, which is, in comparison to the trillion parameter models, that's really small. But in comparison to edge devices, it's not something that you can really still even run locally unless you have a very, very, very beefy GPU. I think the very, very high-end commercial GPUs, I think might run a model that big, or small, but edge devices, probably not. And again, a vehicle is designed to be really efficient. I know what probably some of you are saying is, like, what about autonomous vehicles? Well, most of those have an actual giant compute node somewhere in the vehicle somewhere. Now, there's still, the jury is out whether the autonomous vehicle approach, how that's going to scale long term in terms of efficiency of compute, energy, and commercial considerations. So yes, there is a lot of compute on board one of those vehicles, but that's also being subsidized right now by the Googles and the Amazons who believe this is a 10, 20-year battle to bring this to market and are willing to spend that kind of money. So, and pretty much any other application, the reality is if we want to be able to use AI with these systems, we need a way to get that data on the vehicle, off the vehicle.
So there's a question in the chat around how do you stay sustainable in this model, ethically, economically, and environmentally. I think it's driving to that point, right? So if you want to address that, and then I have a question as well, but I'll let you address that one first.
So I'm sorry. So is that about autonomous vehicles or?
Yeah, it would be.
Or is that just about AI in general? I also I didn't. Can you go over that one again? What were all the points that I heard ethically? And okay,
Yes, as you scale. As you scale, yes. How does that? AI in general, as we scale this up, the model training is going to take a lot of energy, right? That's the constraint on these chips. Everybody wants GPUs, get the GPUs. Now I got to power them to do the training. We're sending a lot more data. We're doing a lot more processing, right? How does this impact the environment and the economics, right? Everybody's electric bills going up because data centers are sucking us dry and things like that, I think is the point.
I, you really want me to solve you really want me to solve all the world's problems right here, don't you?
No, but we want you to make sure you have guardrails in place, right? You want to have
Well,
some thoughts around this, I think is the concern. And sure.
this was part of our thinking behind TrustGraph from the beginning. So TrustGraph we open source a little over a year ago, and using small models. There's a reason why we have end-to-end tests to try to figure out what's the smallest model that will work with TrustGraph, because we really believe that, yeah, we believe. I think I'm trying to think. Do I want to speak for Mark on this, or is he okay? I believe world according to me. I don't want to speak totally for Mark. Uh, that there's a big divide between what I see in consumer AI and enterprise AI. I think consumer AI are going to be the Chat GPTs, the Claudes, the Geminis, the Perplexities, which are going to rely on cloud-based compute, and because it has to have that scale, because you have people all over the world that are connecting through multitudes of devices. Kind of what we were saying before. You're talking about where you have very little control except at the application layer. So that's you're going to be your solution. You're going to need lots of compute. You're going to need to do it that way. We don't believe enterprises are going to look at it that way. We believe enterprises are going to want much more control over the models. And the way you really do that is deploying your own. You take open models where you can evaluate the training data set so that you know what's been in the model, what's lurking in the embeddings, and that's where you start tuning systems around these smaller models, which you manage the deployment of. And that was it was really hard. It's still really hard. And I say that because we did that. That's something else that TrustGraph does is actually can manage those LLM deployments on bare metal so that you're not just deploying this full agentic stack of services from Pulsar to how you ingest data and knowledge graphs, et cetera, but being able to deploy these models that you have control over. And these don't require, I always forget what the latest NVIDIA is, a Blackwell, the B200s. They don't require B200s. You can get away. Actually, I think Mark, co-founder of TrustGraph, he did an event, a talk a couple of weeks ago where he was talking about using a consumer grade AMD GPU that was several generations old and can run models like Mistral 12B Nemo on it and get great value from it. And that's where we believe enterprise is going for kind of all the reasons that you talked about, is that, efficiency, energy, corporations, whether they're ethical or not, they worry about the public perception of it with ESG concerns. So it really gets down to the bottom line, though, is that it's much more efficient to do it this way. And consumer solutions tend to be more inefficient. We look at how Google and Meta design their stacks, and they're allowed to kind of print money because they're in the advertising business. They sell advertising. For everybody else that's not selling advertising, you have to be a lot more diligent about how your solutions are designed. So I don't know if that fully answers your question, but I think that enterprises already aren't really thinking that way. They're already looking for being more efficient, not just from a compliance standpoint. They have lots of compliance requirements around data sovereignty, data privacy, how they comply with all the regulations around the world. But again, just they're looking at the raw numbers, and they're looking at, am I going to spend millions of dollars of tokens with OpenAI next year and not really know what I'm going to spend? Or am I going to deploy a solution where I know exactly what my spend is going to be because I control it down to the compute layer?
Mhm. Right.
Did that answer that one? Or are there any more questions, or should or do we want to come back to the questions later?
No, that looks like it's good. We can do questions at the end
Okay.
as well as one I just brought up. So I'll let you continue.
Okay.
So we're bridging the gap between DSS and going onto the internet, and they want to interrupt your flow. So how does this solve the data silo problem and get
So
us from the car? Yeah, please.
the way we solve the data silo problem is with knowledge graphs. And that's a term which um, sometimes you don't hear the word knowledge. Sometimes you just hear graph. I see this term get used a lot of different ways today. Uh, I mean, just a brief history of knowledge graphs, again, not new, have been around for, you can find references to that architecture in going all the way back to the 90s. It's just a different way of structuring data. Instead of just having tabular data where you have, a row and columns, knowledge graph structured data in today, the standard is subject, predicate, well, I'm trying to get it backwards. Subject, predicate, object. So you get information relationships. And as you can imagine, you can have this be as complex or as simple as you want. You can create hierarchies, you can create attributes, you can get properties. Some people consider you have some graph structures which are known just as property graphs. If you've ever worked with Neo4j, that's a good example of a property graph. TrustGraph actually has our default is Apache Cassandra, and we use a different way of structuring, which is known as RDF, which is not necessarily a property graph. It allows you to have property graphs. And now I'm talking about knowledge graphs. And if there's any knowledge graph people in here, the chat will explode with very incendiary comments, because it's a community where people have very, very strong opinions, very strong. And I guess we do too. We think that all of these have their use cases. But for unstructured data, this is the optimal way of structuring it. And you're thinking, well, why haven't people done this before? Because before LLMs, it actually just took too long. If we go back to my story about the pain I suffered with the engine generator problem for a C-130J, you have all these documents that are in different places, and we were having to read them manually. To build a knowledge graph from that, somebody would have had to have manually done that as well, which that's a huge amount of time. How do you justify all that? Well, now we have data ingest pipelines that can build these graphs and capture these relationships autonomously and get that data into these graphs. So we can all of a sudden point TrustGraph at tens of thousands of documents, and it's going to build these structured graphs for us. And all that data will be managed by Pulsar, of course. But this is actually something we really couldn't do. Even a few years ago, people were trying to do this with NLP models, natural language processing. It had limitations. This is really something that's only been possible. It's something people have been wanting to do for decades. The desire has been there. It's just now the technology is catching up. We have the compute, and we have the data, the compute, and now the models. And the compute and the data are what enabled the models to now be able to structure our data in a way that we've been wanting to do it really since we started creating data. Mm-hmm. And that's really what we're talking about doing here, is that we take all of this data and we're able to structure it in knowledge graphs that enrich it. It builds those relationships so that we now understand how a maintenance process relates to how one maintainer followed the process and it didn't work, and then why it didn't, and how that relates to a different process, how that relates to a different aircraft at a different point in time, so that now, instead of 3 people sitting around for weeks reading reports and then going, hey, what did you find? Did you find this? Somebody could ask an LLM to retrieve this, and all this information is now in front of them in less than a minute. So again, this is things that we've been wanting to do for a very long time that just now have been become possible. And kind of trying to bring this back to fleet operations, if you operate fleets of vehicles and instead of spending weeks with people reading reports trying to figure out why their vehicle has an error code, if you can solve that problem in a matter of minutes now, that is absolute massive business value because fleets of vehicles, uptime, vehicle availability is the number one concern. So any way that you can reduce maintenance, that you can improve reliability, efficiency is a massive, massive win. And this is us. TrustGraph is open source. It is built with Pulsar, has been from day one. And as I said, we can deploy it anywhere, whether it's locally on your laptop, on-prem, cloud. We can even manage the LLM deployments as well. So that's a little bit about us. There's got to be questions.
And
How about you, David? Do you have any questions?
I do have some questions. You mentioned, so what intrigued me was you showing the bridge between DSS, the on-vehicle sort of scenario, over to the cloud scenario. Can you give me an example of a connected vehicle feature that would demonstrate that complete loop where you would actually need from the telemetry collection, cloud AI processing, and an actionable response back to the vehicle? What's
Oh,
the use case for that?
so there's a lot. It depends on how deep you want to go on that. Um,
Mhm.
I I think this in this problem space, I think we want to. I don't. I think we have to be realistic about the starting points. This is kind of why I use the maintenance one as a good starting point. I think
Mhm.
we need to get data off first
Mhm.
because it's the time issue that worries me. I think that we're going to have to look at real time data and we're going to have to look at how we. There's either we can bucket the data and start creating, time slices of there's data within this 50 microsecond window, and we start evaluating, what was the steering angle during this 50 microsecond window,
Mhm.
and what was its average, or what were the trends? Um, because again, you're talking about point in time data for other technology that just can't respond on its time scale.
Mhm.
So I think that we start first by pulling data that doesn't necessarily require that time granularity. That how does the data coming off impact data that we already know about the system?
Mhm.
I think that problem has to be solved first before we start pushing back. Because imagine you say, I want to use an LLM. Say
Mhm.
you work like at a Waymo or Zeus, and you're in one of their remote centers that's actually monitoring the vehicles at all time, and you want to have your operators be able to issue a voice command that's then going to affect how the vehicle operates. Well,
Mhm.
that sounds amazing, but if we're talking about, hey, turn left right now, how long is it actually going to take for the LLMs to process it locally and then get that over networks to then get to the vehicle and then be executed? The vehicle might have already went into a building by then.
Mhm.
So this really gets back to quality of service, and we're going to have to start thinking about that, off vehicles as well. What are our tiered qualities of service? What are the most important data down to things that are just best effort? And those lower levels are where we need to be playing for the near future, the near term. But there's a lot of business value that can be driven there.
Yeah.
Really start, yeah, that's where we start is those lower levels of quality of service.
I was gonna say Michael put it in the chat. He must have read my mind. A lot of mind reading going on today. He said automatic traffic rerouting would be a good use case. Collect information speed from a lot of different cars, trends for slowdowns, and reroute them automatically. Because my use case is the same as like I use Waze all the time, Google Maps, and it has a person in the loop, right? It tells me, hey, there's a slowdown here, pick a different route, or hey, there's a speed trap up ahead.
Mhm.
If that can just embed back into my car to say slow down or change routes, right? To say, hey, don't go this way. There's an accident on the freeway. Go this way. Into that, that could be an example use case. I guess that was something
Well,
that
no,
popped in mind.
that's a very important one. Actually, I
Right.
see that Mark is in the chat. So Mark and I were both at Lyft. Actually, Lyft acquired Mark's company, Trust Networks, back in 2018. And routing is really important for rideshare because if they don't have a passenger in the vehicle, nobody's making money. The drivers aren't making money. Lyft and Uber aren't making money.
Mhm.
So routing, everybody knows the classic example of UPS. They only make right turns because it's more efficient, because you don't have to wait on a red light to make a left turn. So their routing is designed around making all right turns. So if you're operating fleets of a vehicle that has that scale word, then routing very, very, very important. And again, that's a great use case where you can say, hey, there's an accident up ahead. Um, we're going to have to take, a different route. And, as an individual, we don't think of these things as being, life or death, or critical. But
Mhm.
if you're operating a fleet of vehicles and all of a sudden 100 vehicles are impacted and waste 30 minutes, well, that's 100 times 30. You start doing the math, it's dollars. It's real dollars.
Mhm. So a question popped up
Mhm.
from Francis in the chat. Could you use event data such as braking, stopping, acceleration, right turn, left turn as an example of creating relationships as you described in the subject predicate objects in that case?
Oh, that's an interesting one. And as I said, knowledge graph. I wish Mark was actually on this. He would probably have a better answer because Mark's the knowledge graph expert. I would say that it's yes and no, in that, that's a pretty good example of, tabular data, in that, acceleration is X, it's a number. And for every single update, there's just a new number. Now,
Mhm.
however, when you go to the knowledge graph, and you look up the term acceleration, you would have a lot of data about what acceleration means, from the definition of what is acceleration to what are the standards that define requirements for acceleration? What are acceptable values for acceleration? What if the acceleration is this value and these other situations are true? That's really where the knowledge graph would come into question. Is would bring you value, is being able to find. It would be where the acceleration is related to other other areas. So you would have the tabular data, and you would have values and ranges associated with that in the knowledge graph. Right. Yeah. I think. Yeah. It's a little bit of both. A little bit of column A, a little bit of column B, and that's why this is a challenging. Real time data is very challenging,
Mhm.
and I think that it's going to be, again. This is going to take. This is not going to be a simple path to really leverage AI with this sort of data. It's going to have to be a step by step process. We build those bridges. We get access to that data. We then start thinking about how can we make sense of this data using this new technology in ways that aren't safety critical, in which there aren't potentially severe negative outcomes from maybe just having the response be too slow.
Yeah, absolutely. I think Mark joined and he mentioned made a comment on break data is kind of raw. You can do a lot with that data, but usually to get more intelligent views of the data for knowledge graphs, right? So it's something that I guess it needs to be refined into intelligence versus raw numbers, sort of thing. Would you like to build on that at all, or that point that Mark made, or
Well, I think
agree
that
with them?
there's a lot of different ways that you can think about this. And that, as I see Mike just talking about breaking events, you can So you start accumulating data about how many breaking events happened on the interstate in certain situations. And then you can start doing things like, risk assessments, because risk assessments are not just one number. You have to describe a scenario, and then you have to think about, what's the likelihood of this scenario? What are the consequences of this scenario? And that's mostly all text. It's not just hard data. So that sort of data then becomes useful for doing all sorts of things that are very, very manual before. Actually, should I stop sharing? So it just
Yeah.
let's do it this way. So it actually looks like you and me again, David. Um, um, so that enables us to do a lot of other things that would be very, very manual before, is being able to get access to that data. And again, as these systems mature, as we improve them, there's a lot of potential on how we can start structuring even that kind of data in more intelligent ways.
Yeah, you could start using it for urban planning. What sort of areas have congestion? You look at things of, speeders or frequency of accidents, things that are dangerous, and detect patterns from that raw data that you probably didn't see before.
Right.
Staffing,
And,
things like that. Yeah, police out
and
there, whatever.
right. I mean, that's actually the concept. So Toyota has an initiative called Woven Planet, that was a concept of actually building a smart city from the ground up in Japan for exactly this purpose, is that modern cities, at least here in the US, well, I guess we don't really have modern cities in the US. All of our cities, the planning goes back decades, which, didn't have autonomous vehicles, didn't even have cloud, didn't have the internet. We didn't have lots of things. And the idea being that to leverage these new technologies, we really have to think about urban planning in a very different way. And then to think about urban planning, we need to think about lots of human concerns, which don't really, you can't really put a number, a raw data number on. You have to, how does this impact people's lives? Again, you think of kind of like a risk-based approach. What's the value that comes from this? Lots and lots of intangibles that we would describe with text. So all things that potentially with AI technology, we could start doing in a much better way, much quicker way, so that we might be able to come up with these plans instead of years. We might be able to reduce it down to a number of months, because AI would allow us to iterate through all of these permutations, where people before were, their heads down reading reports for weeks at a time.
Mm-hmm. Well, yeah, this is great stuff. So I know we're at time. I appreciate you taking a whole hour. I knew it'd be a very interesting subject. So thank you everyone for attending. We're gonna go ahead and wrap this up now. And if there's no other questions in the chat, we look forward to this being recorded and available online. So thanks again, Daniel, for your time. We appreciate it. Always educational speaking with you. And thank you everyone for attending. Thank you so much.
Thanks for having me, David.